Hi, my name is Sam Ackerman. I'm from IBM Research in Haifa, Israel, and I'm going to talk about machine learning model drift detection via weak data slices. These are with my co-authors from IBM. So say we have a data set DJ with NJ observations. A classifier model has been trained on this data set to predict a label feature Y. The model makes MJ misclassifications, or MCs, on the data set DJ. M over N is the misclassification rate, or MCR, of the model. Here we have a toy data set with three features: age, state, and sex. There's a red column incorrect, which is a 1 if the model made an incorrect classification on that observation. So here we have N is 10. There's 6 misclassifications, so it's M. The MCR is 0.6. Our tool, FreeAI, creates interpretable data slice rules. Slice is, for example, a region where age is between 18 and 25, and state is either California or New York. Observations in these slices will have a higher MCR in them than the data overall, and this is called we call these weak areas. We return these to the user to diagnose the model. So, for example, here this slice has on this data set has 4 observations with the orange boxes. So that's N1. The MCR here is 0.75 because there's 3 incorrect out of 4, and that's higher than the 0.6 overall. And this is only using 2 of the features and not the sex feature. And the great part about our tool is that it can work on any classifier type, since it only uses the indicator of whether it was incorrect or not. It doesn't have to use any underlying information about how the classifier itself works. Say we have now multiple data set slices. So for example, S2 and S3, these are blue and green. These are shown by the boxes with the dashed blue or green lines through them. Here you'll notice, for example, rows 1 and 3 appear in both the orange and the blue, and row 9 does not appear in any slice. The yellow shades any observations that are any of the slices. So you can have both overlap of observations in slices and also missed coverage where an observation doesn't belong in any slice, and we want to avoid that, hopefully. So say now, for the purpose of drift testing, which I'll describe in a second, say we have the 2 data sets, and we can take the slices from D1 and map them to D2, and that's basically figuring out which observations in D2 belong to each slice from D1. So for example, the orange slice now has 5 observations rather than 4. And what we'll do is, for each slice, we'll calculate denoted by pi ji. It's the fraction of the observations in the data set contained in that slice I. So we'll compare between the two data sets the fraction in each slice. You'll see, for example, slice 1 changes from 0.4 to 40% to 50%. 2 goes from 20 to 30%, and S3 still stays at 20% of the observations. For drift testing, what drift testing means is that there's some kind of a significant change between the 2 data sets in terms of individual or multi-way feature distributions or associations. And if these 2 data sets are basically from the same population, or say train test splits of some data set that are random, you expect minimal feature drift between them. They should have the same MCR or similar MCR. And if you consider any slice Si from the first data set D1, it's a relative size, and the second data set should be pretty similar, and also should have this similar internal MCR, which we assume is unobserved. So we're assuming that the feature distribution X and the label conditional on the feature distribution does not change, or is pretty similar, and therefore also the probability of making a mistake given the features should also be relatively stable. And in this work, we're interested in detecting these distribution changes, particularly where in these weak regions where the model is likely to have high MCR. We do this via slices because if the slices target these misclassifications, and in our experiments we see that they tend to cover the vast majority of them, then we can see changes in the weak areas through changes in the slices. If for our hypothesis test setup, if there's no drift, like I said, the slice size should be similar. So the difference between them for every slice should be approximately 0. Formally, we'll have a null hypothesis, again, for each slice, h0i, that the slice relative sizes don't change. The difference is 0. And we'll detect drift if between the data sets, if for many slices, their sizes appear to change significantly. And this is done by testing for each slice. We have an alternative hypothesis, HAI. And we have 2 goals in this paper, 2 different things we want to detect. The first one is to detect general distribution change in the data set. So for that, we're saying that the difference in slice sizes, this is alternative hypothesis, can be not equal to 0. Basically, it can either grow or shrink between the data sets. The second goal is to specifically detect that the second data set likely has a higher misclassification rate. In that case, the slice sizes should grow, so the difference should be positive. So that's why the alternative here is one-sided rather than two-sided. And again, this is assuming that the relationship between misclassifications and the feature distributions are stable between the 2 data sets. So if that holds, then on average, slice sizes should grow in the second one if there's a higher MCR. To test this, we use the difference in proportions test on these observed differences. Each hypothesis test gives us this p-value, which expresses the probability that the observed change in the proportions could have happened by random chance. And a low p-value means that this observed change is significant relative to the probability that it didn't change. And because we have 2 different alternative hypotheses, their p-values will be a little bit different for each goal you're trying to test. And again, the p-value kind of probabilistically lets us choose between the alternative and null, where the null is that there's no change for each slice. And a false positive occurs if the slice has by random chance a large size change. The thing is that for our method, we want to detect overall change between the data sets and not individually on the slices. So we'll kind of aggregate the hypothesis test results over all the slices. So we have an overall alternative, a null and an alternative, H0, HA, not the individual slice ones. Because of this area of work called multiple hypothesis testing, it's not enough if just one of the p-values is judged to be significant, or basically one of the slices changed significantly, to say that the data set overall changed, because the probability of making a false decision overall increases with the number of slices or hypotheses that you're testing. So we'll use the family-wise error rate, or FWER, which is a way of quantifying the probability that at least one slice is significant but falsely. And we will use a Holmes adjustment, one way of making the overall decision, looking at the p-values. And this lets you keep the single decision that you're trying to make with a false positive rate below the alpha. So it's statistical correctness of the overall decision of drift. The way we evaluate our method is here I'll only talk about the second goal of detecting MCR, not the first one for time reasons. We take each data set and split it into a test and a train and test, D1 and D2. For 50 times, that's a superscript B, and stratified so that the misclassification rates are equal for each one. The odds ratio phi for a data set is the MCR over 1 minus MCR. So for example, here we have, because there's 6 misclassifications out of 10, the phi, the odds ratio is 6 over 4. 1.5, and when that's the same, we expect the slice sizes to be about the same for each slice between the two data sets. The way we evaluate the method is by creating altered test data sets D2B star with a new higher odds ratio. So it'll have a odds ratio of 5 star be k, a constant multiple k of the original odds ratio, where if k is bigger than 1, it means the MCR is increasing. And we resample observations from the test data set so that it has the altered one has the desired MCR. So for example, the third observation here is resampled twice in the second data set, and the data set size is held fixed. So for example, this altered data set on the right has 9 misclassifications, that's M star, and it'll have a new odds ratio of 9/1, which is 6 times phi, or which was 1.5. So the K multiplier here is 6, and you'll see in this case the orange and blue slices grow, that the green one stays the same. We have 3 data sets that we tested in our paper. Adult, the black, Uneron, the red, and MP, the green. The odds ratio here is shown from 1 to 10 is shown on the x-axis. The y-axis is the resulting MCR. You'll see for k is 1, this shows the initial MCR for each data set. And they tend to differ quite a bit. The red one, Aneron, it started with very low misclassification rate. So it takes a while, like a large multiple of k, to get an absolute change that you can detect, or that you can detect quickly. The other ones with higher MCR initially, you can see they increase a little bit faster when you multiply the odds ratio. The detection rate is the fraction of the 50 splits B, where we're the controlling for the multiple testing, where the altered data set D2B star is detected to its slices overall are larger than the trained data set D1B, which we determine the slices on. And we try this for varying K. And if K is 1, that means that there's actually no increase in the MCR, but we randomly resample, keeping the MCR the same. The detection rate should be about alpha, which means that's the false positive rate. It should be less than alpha actually. And we want to see that here for these 2 data sets, we want to see that when K increases, that the detection rate goes from around 0, where it should be for K is 1, to 100% fairly quickly. So we want to detect for most of the splits, a change fairly quickly. And the left one here is the MP data set, and the right is Uneron. Uneron started with a lower overall MCR, as I showed before, so it takes a higher multiple K to end up detecting it. So there's some effect depending on the data set initial MCR as to how fast you can detect it with this, at least under these simulations. So future improvements, the first one is we want to have to evaluate our slices which target the weak areas, or where there are higher more misclassifications. We want to compare this to a naive baseline of randomly generated slices that don't target them, to show that actually this method with weak slices detects changes, for example, in the MCR better. Second thing is in our multiple testing, we can give higher weight to p-values where the slices are larger, because sometimes maybe a small change in a small slice of maybe one observation might be judged as statistically, but it's not practically significant. Third is there's some theoretical problems with p-value framework, so we can use an effect size metric like Cohen's H, which works on proportions, to judge whether an observed change is actually significant practically. And third thing, the last thing here is instead of, as I said here, we resampled observations from the test data set to create the altered one, so they're duplicates. It might be more realistic to use again and model them to generate new observations rather than using the exact ones.